Greetings, friends. We're going to try a different look today, as if you are floating in midair. How about that? Okay. So what we have is the somewhat beginning of our discussion of electromagnetic waves. After yesterday, we talked about the microscope, we talked about the telescope, we talked about virtual images. And I think that's going to signal the end of our ray optics. We're going to start now to morph into wave optics. So this is the situation where the wavelength is going to begin to matter. If you look back at the intro I gave at the beginning of the optics section a couple of weeks ago, then this is the time when the energies are still low, but the wavelength is near to the size of the objects that we're going to be detecting them with. Okay, but before that, just a quick reminder on PLC. We've got a PLC that's going to be due PLC 8, which is due Friday. And I have homework 5. I just forgot to post that, so that'll be due after spring break. This angle is kind of helping to minimize some of the glare. I should have thought of this a long time ago. Spring break, as you may or may not know, for us here at Cabrillo is going to be this next week, this coming week. All right. So we'll have 3 classes this week. This is class number 2, and we will be off. We'll have a lab this Friday as well. And then we will be off for the following week. And we resume on April 7th. Is that right? Yes, it's April 7th. So we'll pick up that would be the Monday. So we will pick up on the 8th, which will be Tuesday. So after tomorrow, I'll see you for lab on Friday, and then the next time I'll see you is for class on April the 8th. All right, so break, that's next week. All right, so happy spring break to those of you who are on spring break now. Happy spring break to those of you who have spring break next week. And I think that takes care of everybody. So either you have it this week or you have it next week. I think. Well, if you're in this class, you have it next week. So that's at least one thing. All right, so let's get back into talking about electromagnetic waves that we're not back into. Let's start talking about electromagnetic waves. Now, this comprises the second model that we have for light. Light is, after all, an electromagnetic phenomenon. The question of whether it's a wave or not. Well, it was Newton who first put forth the idea, which is called the corpuscular idea, which is the situation in which light is made up of a small stream of particles, corpuscles, as if you're thinking about blood cells or something like that. And it wasn't until about the late 1600s, near 1700, and it wasn't until about the middle to late 1800s that people started saying, no, look at this. Light does the same thing that water does. Water waves do this. Sound waves do this. Light does the same thing. Must be a wave, just like sound waves and water waves. All right. I think I got the wrong set of lights on. Just a sec, let me turn this off, turn those on. All right, I wonder if that helps. Okay, well, we'll see. I definitely think this angle is helping. I'm seeing much less glare, so that's good. So maybe things will be showing up better, and hopefully, thanks to one of you in this class. We hopefully have the sound situation taken care of. So thank your local sound engineer. Let's talk about waves. So we've talked a little bit about the idea of the wavelength, right? So the wavelength we will say is this quantity, lambda. And basically, if I think of a wave, I'm going to draw something that's sinusoidal. If I draw a sinusoidal wave, like so, and I say, okay, wavelength is where? I would typically have said it's peak to peak. In other words, it's the distance it takes the wave to repeat. And we have two different types of wave. In other words, we have a wave which, as this wave is perhaps illustrating, were this wave to be traveling that way at some speed v, and it's oscillating like this, but going this way, right? Its oscillation is perpendicular. It's in a plane which is perpendicular to its travel. You might say that's not true because you've got your hands this way and the V's that way. Well, let me put it this way then. If you think about the wave fronts, they're going to be going like this as they move that way. So how about that instead? The vibration of the wave is up and down as the wave travels this way, and therefore that's called a transverse wave. So the oscillation or the vibration is happening like this, and V is that way. That's the travel. Then we have what's called a transverse wave. And if it happens that the oscillation is in the same direction as the travel of the wave, for example, the up-down vibrations would be jump rope style. Right, so it's the wave is moving down the rope, but the peak and the peaks and the troughs are moving up and down like this. Whereas if I have one of these, this is more like a slinky. If I take a slinky wave and I go like this is also how sound waves transmit. This is along the direction of travel, so this is just going to comprise a longitudinal wave. So light is 100% transverse. Earthquake waves have both of these. Water waves typically have both of these. And what else? Their sound is longitudinal only. Light is transverse only. So there you go. And also we know that the speed of light in a vacuum is the same for all electromagnetic waves, regardless of their frequencies / wavelengths. All right, so for light, the speed is equal to what's known as c, and c, in case you didn't know, is a well-defined number. In fact, it's now a fundamental, well, it's not now, it is a fundamental constant and is defined to be this value, actually slightly less, it's 299.458.792. But nonetheless, we all round it to 3, so it's that many meters per second, and that's in a vacuum. As we've already discussed, light slows down in a material based on its index. So the material's index, you say C divided by N, the C divided by N is a speed in the material, or if you like, C divided by speed in the material is index of the material. And this is regardless of frequency or wavelength, and we also have the kind of fundamental relationship here that the speed of the wave is the wavelength multiplied by the frequency. Okay? This is the frequency of the wave. I've talked about the spectrum of light already, where we've talked about kilometer-long wavelengths, centimeter-long microwaves, millionth of a meter sized infrared waves, hundreds of billionths of a meter, which is visible, into the billionths and tenths of a billionth, which is ultraviolet, into X-rays, and thousandth of a billionth is into the hard X-rays. Millionth of a billionth, well, you've got something like gamma rays at that point. So regardless of frequency or wavelength, they travel at this speed in a vacuum. All right, and if it's air, remember the index of air is essentially 1, so we also say basically more or less to a reasonable approximation, this is also their speed in air. Though I wouldn't say it's this, because that's a little special. I would just say it's the number. Okay, so I'm talking about light as an electromagnetic wave. What does this mean? In case you haven't had 4B, or if you have had 4B, or if you had 4B with me, which I don't think anybody in this class has, hopefully you talked a little bit about electromagnetic waves. What is this? Well, what that means is we have in talking about electricity, we have electrical charges, and the charges have associated with them an electric field. Just as you might say a mass sitting in space has a gravitational field. Earth has a gravitational field, Sun has a gravitational field. Electric charges have an electric field. A moving electric charge has also a magnetic field with it. Okay, so electric field plus magnetic fields okay, is not quite enough to give us an electromagnetic wave. We have to have acceleration, right? We have to accelerate the particles. And in order to do that, we have to supply energy to the particles in order to get them to move back and forth. However, that energy is then radiated away by the charge, because only electric charges that are accelerating, in fact, are going to radiate. All right. So the electric field plus the magnetic field, we call this the electromagnetic field. And what it can do is it can make a wave and oscillate. And so we can talk about some of the things that go on with that. Let's see here. I have a couple of characteristics to tell you, which is to say that if you have, for example, an electric field. So suppose I have a wave traveling this way at speed c. Now, this being a transverse wave, and it's being made up of these two fields, suppose we have an electric field which is oriented that way, and I will denote the electric field with an E vector. Okay, so if I'm trying to draw this in perspective, so if it's traveling this way, the electric field is perpendicular to that motion, right? It's vibrating up and down like this as the wave moves like that. Okay. Now, along with that, we also have a magnetic field. Now, one interesting tidbit about this is that the electric and the magnetic fields are mutually perpendicular. They are at right angles to each other. So I would draw the magnetic portion of this, perhaps something like this, like that, such that they are, so if this is my electric field going, say, straight up and down like that, the magnetic field's going back and forth like this, and the whole shebang is traveling straight towards you. Is that true if I go E, B, sure. If it's like this, right? So if I say E is going like this, B is going like that, and it goes like that, and then it goes like that, and 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 it's approaching you. All right? E is perpendicular to B, and both of these are perpendicular to V, its direction of travel. That's what gives us a transverse wave, right? There's no part of E or B which is pointing in the direction that the wave is moving. Now, furthermore to that, if you know the electric and magnetic fields, you can figure out that they are transporting energy. Okay? You can say, hey, the electric and magnetic fields transport energy from one place to another. Okay? It takes energy from one place to another. That's essentially what radiation is, right? Radiation is a motion. It's a movement of electromagnetic energy from over there to over here. Okay, so the lights are radiating out electromagnetic energy. Some of it we can see, and it's bouncing off the board, and it's bouncing off my head, and it's going into the camera. So it's transporting energy from here to there, and at each point where there's a reflection, there's also a little bit of absorption. Okay, so the wave transports energy, and it does so due to the energy, what's called the energy density of its fields, the electric and magnetic fields. Nonetheless, I'm not going to go into that because that's more a 4B topic, but what we can do is we can calculate how much energy is transported by the light waves. And what we have, it was first discovered by a person by the name of John Henry Poynting. So we have what's called the Poynting vector, which is a really great name for it. The Poynting vector is S, and it tells us the amount of power per area. So it has the units of joules per second for the power, or watts, per area, so for example, per square meter. This is essentially like a radiant flux. Okay? The flux is typically something per area, and if you do a per time in there, it's a power flux. Right? So this is an energy flux per time. It's given as the cross product of E with B. So you can write this as epsilon naught c squared times E cross B. Now, E cross B is a cross product which you'd use your right hand for typically. And if you look at this, I would say, suppose my E is going upwards, my B is coming out of the board like this, so the C, right, the direction of travel is that way. Likewise, when you think about the pen example, if my E is this way and B is this way, then what I have is the ability to, I don't know how you like to do right-hand rule, but I'm going to do fingers in the direction of the first thing listed, so E, curl them in the direction of the second thing listed, B, and then my thumb will point the direction that the energy is going, which is essentially the energy, which is the motion of travel of the wave. Right? So in this case, E, B, that way towards you, it would be going like this. It'd be going like that, and it'd be coming towards you. One interesting thing about this is that, well, so first of all, the cross product describes things that are mutually orthogonal to each other, so that's fine. But one interesting thing about this is that we choose, humanity in general chooses to detect and work with the E field rather than the B field. And one of the reasons why is because the electric field is a larger magnitude field, and so therefore easier to detect. Okay? It turns out that E and B are related in magnitude by C. The effects of the electric field are generally very prominent. The effects of the magnetic field, not so much. It's actually typically usually quite difficult to try and pick up a magnetic variation in the electromagnetic wave. It certainly can be done. It's there, as far as we can tell. But for most practical purposes, if you're talking about radio waves or something like that, and you have these big long antenna, it's because you're accelerating charges with varying electric fields, and the electric fields are going rah, 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 right, and when the charges are going up, down, up, down, up, down, up, down like this, and they're making a wave, It's typically the electric field that we're thinking of as picking up in the antenna. All right, so one of the things that goes along with that is we can talk about the direction of the electric field. What makes it okay to say that the electric field is only going this way? Why couldn't it be going this way? Why couldn't it be going this way? Well, it can. As long as the B field is perpendicular to it at all points and all times, yes, it's fine. So what we come up with here is a direction of the electric field, which we'll talk about in a minute, and the subsequent interesting bits of the wave that you can mess around with the electric field. But hold on that thought for a minute. I want to go to one other thing, which is related to the energy transport issue here. Which is that since the waves carry energy, right, they also do one other thing, and that is that they carry momentum. They also transport momentum. The electromagnetic fields transport momentum. So I'm not sure if I'm going to get this to work in a wonderful fashion here, but I did bring in a demo for you. I'm trying to think about you folks. You're sitting over there on the other side of your computer, probably drinking a coffee or something, and sitting there in your robe and slippers, and we'll just do this. So I'm going to turn this off for a minute. This is an extremely bright light. It's one of those halogen ones. I want it to stay upright for a little while, like so. Okay. The device I would like to show you is basically this tiny thing here. It's a glass globe with a needle sticking out of its center. There's a small protrusion here which is built in, and then a needle which is coming out of that, on top of which is balanced this essentially windmill looking thing with black and white sides to it. Okay, and I know it's a little bit hard to see because of the lights, but anyways, you can maybe see a little bit better if I cover this over a little bit, and you can see there's black on that side, and there should be white over here. It's, you can't hardly, well, maybe you can see it a little better if I don't do that. It's actually easier to see. Interesting. All right, well, anyways, the veins are blackened on one side, white on the other side, and they can rotate very easily. As you can see, I can jiggle this thing and it can kind of get it to start going. So this is a very well balanced thing here, and I'm going to try and show you that when light hits a surface, it can be modeled as a collision, just like we have done in 4A with momentum. We can model a collision between the electromagnetic wave and the momentum it carries and this thing here. So take a look. I'm going to put this up a little bit higher, but that's going to blast me right in the face. All right, let's see if I can hold this here and get it to stop moving. About like that, almost. Okay, now I'm going to hold it in front of the light. Oh, here, I know what I'm going to do. I'm going to go like this. And lo and behold, it gets going pretty good. So here I'm going to blast it again with some light. And hopefully you can see that's moving around pretty well. That's a pretty good. Wow, if this was a windmill, this thing would be kicking out a ton of electricity. answer to why this is happening involves the momentum. So the electromagnetic waves take the momentum, they transport it out of the accelerating charges in the filaments of the light bulb, and they take it across space and it hits this surface. Now, remember, we talked about radiation, and we talked about black body radiation. We talked about the idea that when light hits a surface that is dark, right, our supposed black body, right, here comes our wave like this. It's coming in this way. It's going to hit the black surface of these things and absorb. Okay, because if you recall, the black body is a perfect absorber and a perfect radiator. Okay? So it's going to absorb all of this, let's come this way, all of this light that's incident upon it. Okay, will it radiate it? Yes, but if you think about the momentum, the wave here had some momentum, right? It had some momentum going into that side of the weather vane, and then it got absorbed, right? So it basically gave up all that momentum to that paddle of the weather vane, right? So the weather vane then turns, right? And now remember, we had a black side on one side and a white side on the other side. So it turns, and now the white side is facing. Okay, and now what's happening? Now I'm going to take the same thing here. Here comes the wave. It has P going in, and now it's going into into the white side of the vane. Okay, so it hits. But what does it do? If it's a white, it reflects, right? So this is now going to bounce off. It's going to turn around, and it's going to be outgoing. I'm going to put the P, I'll just put the P up here. And now it's going to come out. And I have got that slightly wrong because I am a little pedantic about this. I'm going to go ahead and get this right. Like so. So this is the outgoing wave, and it still carries the same momentum. Therefore, when it absorbs here, the change in momentum is essentially the final momentum minus the initial momentum, right? And so the final momentum of the wave is basically zero. It's been absorbed by the weather vane, right? It's approximately zero, but this reflects, and therefore the change in momentum of the wave now is approximately 2p, because it was initially that way, finally this way. And if you remember how to add and subtract vectors, I only get 0 if I subtract this from this. If I subtract this from this, then I get something that's twice as big as one of these. Therefore, it exerts a bigger force on the whiter side of the weather vane paddles, right? And so you probably can't see, but it pushes the white side more with more of a punch than it does the darker side. That means it turns in a way such that when the light wave reflects off, that side gets pushed. The black side over here hits, absorbs, but it's not as big of a push. Okay? So from this, because this force, by Newton's second law, this results in a force. This results in a force on the weather vane paddle. And this is going to result in twice the force on the weather vane paddle, because the force is related to the change in momentum. If we can put this into a kind of a pressure, or we're kind of relate this to a pressure, right? A pressure is a force per area. pressure is a force per area. And since the wave is transporting energy, we can just write that in terms of the energy it's transporting and the c constants. Because for an electromagnetic wave, we find out that P is equal to the energy of the wave divided by c. In other words, the momentum of the wave that the wave is carrying is related to the energy of the wave divided by c. And therefore, what we can do is rewrite this. Since the force is a delta P over delta T, and the area is area, then I can say, well, this is like a change in the energy per time divided by area and divided by c. Right? Well, I just erased the thing that we were talking about, which is basically this quantity right here. That quantity right there is the Poynting vector. It's the energy per time, right? It's the power per area. That thing is the Poynting vector. It's also referred to as the intensity. That's S, which is the Poynting vector. And is also referred to as the intensity. So this can be written as the intensity divided by c for a situation in which the electromagnetic wave is absorbed. Therefore, I have the ability to define a pressure exerted by radiation. The pressure exerted by radiation is the intensity divided by c if the radiation is absorbed. If the radiation is reflected, then I think I should be able to convince you through the exact same argument that the pressure of this radiation when reflected is twice what it was when absorbed. Okay, so I'm going to say here that the pressure of the radiation is now 2I divided by c. Okay? So yes, it sometimes is a hard thing to get your mind around. The light carries energy, that's not so big of a deal, but the fact that it carries momentum, that causes a lot of consternation for people. I will say that when we get to the photon picture, this is, I think, going to be much easier to digest. Because in the photon model, you're thinking about small little pieces of light moving and then hitting and then bouncing off. And it really is very much like a collision with between two things, just like it was in 4A, when you have momentum of a thrown ball and it hits this other ball or a sail or something over here and it causes this to go this way and it bounces off this way, right? So this very much is a collision type of thinking that we have here. Works really well with the photon model. The wave model, it's a little bit more ambiguous, but nonetheless still here and still reasonably describable. Okay, now, pursuant to this, you might say, what use is this? Well, NASA has used this as a method for propulsion, right? If you take a spacecraft and you want it to go for a really long distance, you're going to send it out to who knows where, right? There is sunlight in the solar system, at least I'm told. It's relatively cloudy today, so I'm not entirely sure the sun's up because I can't see it, so I need evidence. Nonetheless, suppose that the sun emits large amounts of radiation. Maybe it does, maybe it doesn't, who's to say? But if we were to put up a space vehicle with a large sail that was shiny and rather reflective, then the sun would be able to look at its own image and go, gosh, I'm looking good today, aren't I? But not only that, the sunlight would be bouncing off the sail and then providing momentum to the vehicle. And this is an actually viable thing to do. Okay. So yes, NASA has investigated that, and it is it is something that will work. All right, that amount of stuff that's pushed out by the sun is known as the solar wind. It is the confluence of all of the charged electrical particles as well as the photons that are coming out of the sun and blasting everything. Okay. Now, if you're a very small piece of material in the solar system, you will experience this type of pressure pushing you, right? Continuously away and away and away. All right, so this is known as the radiation pressure. I'll put the word radiation above it. Okay, but the radiation pressure would be that. Okay. Now, I want to go back to the idea that the electric field can be oriented in different directions. Okay, so if the electric field can be oriented in different directions, that means that we have different ways of transmitting it and receiving it. Okay, this is known as polarization. Polarization of EM waves. The word polarization, once again, if you've taken the electricity magnetism course, you will have run into polarization as something in which you are separating electric charges from one another. The positives over here, the negatives over here. This is not that. This is something that's different from that. Nonetheless, it does give rise to an electric field which could be oriented in different directions, but it is different from the phenomenon that you talked about in 4B, or whatever the class was that you took, if you've had that electricity magnetism course. So this results in, this is a result of the oscillation of the electric field. It's essentially the oscillation plane of the E field. And like I said, we concentrate primarily on the E field rather than the B field, because it's just so much easier to detect, right? It's bigger, and we have all our instruments are kind of already made to find this. It's much easier. Now, we have light emitted by things like the sun and overhead lights and signs and headlights and other things almost all over the place. Right? Well, we have to, because otherwise we can't really see very well. So, typically when you are emitting light, it is random which direction the light is going to emerge with its electric field direction pointing, right? It's going to be a random direction. So if I take, for example, an incandescent bulb like this one that I was just using on the radiation vane. If I take something like that and I look at the light that's coming out of it and I say, and I go ask individual waves, which you can't, but nonetheless, if I say, hey, what's your polarization direction? In other words, which way is your electric field pointing? Oh, well, it's going that way. Okay, what about this one? Okay, that's going this way. What about that one's going this way? It's going this way. It's going that way, that way, that way, that way, that way, that way. Right? They will be randomly oriented, okay, as they all come out. So we refer to this as unpolarized light. It's not that something's canceling out. Okay, I don't want to give that impression because they're all going in random orientations, and therefore you say, well, it's got a net zero. That's not really the case, because the waves aren't summing. Okay, we're not adding the wave polarizations together. What we're doing is we're looking at when I see polarization from this one, this one, this one, this one, this one, I note that they are in all different directions, not that I add them together. Okay, so typical light is unpolarized. So usually in nature you find unpolarized light. Usually,
Not always, usually. All right? So typical light, which consists of things from natural sources, the sun, right? If it's a source of light, the light coming out of that thing will be unpolarized. Right? Typical light, natural, will be unpolarized. And what that means is, in a diagram, that means that the electric field vector is just going all over the place. Right? I run into E fields, which are just randomly oriented. All right? A source of light that is polarized will have a single or a couple that are all near each other, such that the electric field, we could say, is all going, say, this way, or it's all going that way, or it's all going this way, or something like that. Okay. Right? Contrast that with polarized light over here. And we would say something like this for polarized light. Okay, that would be its E field. And we'd say, there it is. That's it. Okay. Doesn't have to be vertical, could be horizontal, could be 45 degrees, could be whatever. But the point is that there's one direction, right? Up and down. There's one plane in which the electric field oscillates. Whereas, and that means for every wave that's emitted, right? It's all coming out exactly the same. It's all coming out such that the electric field is doing this as it's emitted this way. Whereas in this situation, the light's emitted and this electric field's going like this. But then this light's emitted and that electric field's going like this. And this one's emitted and it's going like this. And that one's emitted and it's going like that, right? So that's what it means when it's randomly oriented. This is an interesting thing because there are some interesting consequences that happen when we make a material or find an interaction in which some of the light is absorbed because its polarization doesn't match. Okay, so this gives rise to the material known as Polaroid. A Polaroid filter is something that absorbs all other types of polarization except one. Okay? So if I take unpolarized light and I put it through a Polaroid filter, okay? Now remember, the electric field is a vector. So if I take a Polaroid filter and suppose that this Polaroid filter, suppose this light's traveling this way, so I'll draw the Polaroid filter right here. And this light is about to hit a Polaroid filter. And let's suppose, let's make a better Polaroid than that. Let's suppose that this Polaroid was going to allow vertically polarized light in it, through it, sorry. Such that if this unpolarized light comes this way towards the filter, then it leaves like this. Does that make sense? Good. Any questions? No? Okay, guess we'll keep going. Now, remember that the electric field is a vector, so that if the light is polarized vertically, and this is a vertical Polaroid, then it'll pass through. And if you're looking at the horizontal polarized, if you're looking at a wave that has horizontal polarization, then it'll get blocked. Okay. What about the one at 45 degrees? Right? What if it's at 45 degrees? Well, part of that is vertical. That will go through. Part of that is horizontal, and that's going to get blocked. So you have to also think about vectors and the directionality. So anything that's not completely horizontal will have a small component or a large component. You will have some part of it that will make it through. All right. Likewise, PHYS, you can think of all of the radiation being partly vertical and partly horizontal. And since it's randomly oriented, then what we can do is look at the intensity of the light here versus the intensity of the light here after the Polaroid. And if this is unpolarized light, I'm going to call this has an intensity of, say, I sub 0 here, I naught. Once it leaves this, because of the random orientation of the polarizations of the waves, then you might as well be able to say that half of them are doing one thing and half of them are doing another thing. In other words, the most common polarization, if it's random, is 45 degrees. Okay? Because that's halfway between this way and this way. And if it's random, then there's no preference between this, or anything in between. Therefore, it all kind of averages to be 45 degrees. Since the cosine of 45 degrees, right? If I think of the situation in which I have a whole bunch of vectors, all right, and I want to pick out only the ones that are going to give me only the parts that are going to be up and down, then I'm going to take the you can think of it like this, right? It turns out that I'm going to be able to take the vertical parts of each one of these vectors here, but I'm going to block the horizontal ones. And because there's an angle, then what I end up finding is that anything that's exactly parallel with the filter and the direction of the Polaroid filter should go straight through with no problem. But if it's off a little bit, it's going to start blocking. The filter will start blocking some of the light because that light has a slight horizontal component to it. Okay. So if I measure the angle of the light and its polarization, if I measure the angle, how far away that polarization vector is from the Polaroid axis, that would be this angle right here. Say here to here, theta. And if theta is 0, that means the Polaroid filter and the polarization of the light are completely lined up and it will pass directly through. Okay. If it's off, then it's going to get some of it blocked. If it's completely horizontal, and these two things are at 90 degrees to each other, then it will get blocked completely. If I'm thinking about the intensity out here, then can you see that it's going to depend on the cosine of this angle? The cosine of this angle is the one that's going to pick out the component that is more parallel with the filter's axis, right? With this, say. Okay. So this is going to equal I naught times cosine, but that cosine is going to get squared. As it goes through. And the reason for that is because the cosine of 45 is 1 over the square root of 2. And therefore, if I square that, it becomes 1/2. And that means that when I take unpolarized light and I transmit it through a Polaroid, it should come out at 1/2 the intensity. Okay. Then the intensity I detect is 1/2 of the incident. Okay. And that comes out of this kind of rule. And I believe this is called a law, but it shouldn't really be. It's really a rule. It's Malice's rule. Law of Malice. And that's not malice, it's malus. Okay, now this cosine rule will always work. Okay, this is a special. I'm hoping to convince you that this is a special case of this. Now, the 1/2 rule is always in play if the incident light is unpolarized. I cannot use this little cute rule if my incoming light is already polarized. Then I have to go to the cosine squared rule. Okay? So that if I have light that's going into a filter that's already polarized, I have to think about what's the intensity of the already polarized light as it goes on this side. How much am I going to get on this side?
And it depends on how far away from the Polaroid axis is the polarization vector of the wave. All right. So to give you an idea of this, well, I can't really give you a very good idea of this. Oh, maybe I can. All right, let's see here. But I would need, oh, there it is. Let me see if I can do this.
Let's see how well this works. That looks like it came out of nowhere. That's funny. It looks like it's floating right in here, but it's not really. It's on the board. Cool. While we wait for this to happen, there's that. Interesting. I wonder if I can. Okay, well, we'll play with that. I'm going to start with doing this. Now, I don't know how well this is going to work. It's going to be quite bright, and what's likely going to happen is there's going to be a suppression in the camera. But if I take this thing, you're probably not going to see too much of a difference if I go like this. Oh, you kind of do. So that's me blocking half the light with my Polaroid. This is my Polaroid sheet here. Right? So if I just shine this thing on here like that, and I say, well, I'm going to now put this in front of the camera. Let's see. That blocks half the light, supposedly. I don't have an intensity detector, but you can definitely see it's reduced. Okay, and so that's not only, I have it this way, and maybe you can see I've got the Polaroid axis marked here. So if I rotate it this way, nothing happens, right? If I go like this, and I rotate around, oh, that's interesting. That's very interesting. All right. So that's the 1/2 rule. Okay. Whew. Let's see, give our eyes a minute to adjust here. Whoa, those things are pretty bright. All right, I'm going to take this and turn these back on here. Oh, good. Oh, good. Let's see if I can do this. I don't care if you, oh, you can't see that part anyway. Go ahead and use the QR code if you like. Let's see what's going to happen if I hold this thing in front of the white light here.
Oh, look at that. Can you see that I'm holding this up here? Can you see this is magenta color? So that I find that interesting. And what's more is if I do this, right, my white light has turned magenta. If I do this, it's turned green. Isn't that interesting? Oops, if I hold it up far enough here, if I hold it up like this, right? No tricks. Just taking the same Polaroid sheet and turning it. So what this is getting at is this is polarized light. And the magenta is polarized which way? This way. And the green is polarized this way. Isn't that interesting? So what they're doing, and this is a bit of a dive into color vision, which I think we'll talk about not right away, but maybe in a little bit later. They're fooling your eye because they're saying, oh, if we add magenta to green, it looks white. So we save a lot of money because all we need to do in our projector is come up with a magenta bulb and a green bulb. I don't need a particularly blue or a yellow or a green, whatever. I do need a green. We only need two bulbs. We only need two colors. And and I don't know why they chose to polarize them. That's a different question, I guess. But maybe it's just the way the light is being made. But that's interesting, right? That's interesting. It's just one way this way, one way that way. Now, it just so happens that I brought in another Polaroid sheet here. And so my first question is then, if I take these two and I put them together like this, what do you expect to happen when I block this light with the Polaroid sheets? I put them together. Well, oops, this way. Nothing. Oh. Well, you can't see up there. I want that screen back. All right, let's put you upwards because there's a little bit of white light up there. Okay, so it's up here. Nothing happens because the axes of the Polaroids are parallel. If I switch them this way though, and I hold them up, now I'm blocking not just one, right? Light's coming in that's polarized this way, and this one's getting blocked, and then that one's getting blocked. So this is blocking everything. You should be seeing nothing. And if I move them this way and this way, you can see I've got a green up top and a purple over here. Where's the purple? Over there, right? I've got a green up top and a purple. So once I block one and I block the other, nothing's left, so that's the end of it, okay? And that would be true also with regularly unpolarized light, okay? Now let's turn this thing off. So perhaps some of you have Polaroid sunglasses made out of these things. Actually really good because when you're, for example, at the gas station and you have your Polaroid sunglasses on, if you look at the LCD display, then and you kind of rotate right, or it's depends how you want to look when you're at the gas station. But if you don't mind kind of standing in front of the gas display and going like this, you'll see it dimming. And the same probably if you have a newer car. Same is probably true with the display, the gauges. Typically the lights will be somewhat polarized. Let's see if I can do one other thing here. Now I'm going to go back to my initially unpolarized light, which means we're all going to get blasted with light here. And now I'm going to take this one and I'm going to go here with it. And now I'm going to take this one, and you can see that hopefully if I go this way, it's going through, and if I go this way, it's not. And in fact, what you're doing is you're seeing a reflection off the screens. So I'm still blocking all the unpolarized light, which I should be able to do with crossed filters. Okay. All right. So if we take a look at, for example, so the idea here is the cosine squared rule. So if I take, say, unpolarized light, and I have two Polaroid filters. Suppose I have unpolarized light, and I'm going to say it's coming along an axis like this, coming from top to bottom this way. I'm going to have a Polaroid filter, say, here, and a Polaroid filter, say, here. Okay, initially the light is unpolarized, so I'm going to draw in what the polarization vectors are. This is polarized, this is unpolarized. So I'm just going to do that for unpolarized light. It's got components which are this way, it's got components which are this way. What else is there? I mean, that's an orthonormal basis, so we don't really need anything else. I don't need to show you there's a 45 or a 30 degree or a 60 degree one on here, because I can take all the components and lump them either this way or this way. Okay, so this is the symbol for unpolarized light. Make that a little darker so you can see that I've got the cross here. All right, so this is unpolarized light. It's going to go through my first filter. The first filter, say, is oriented, that's an arrow. My first filter is, say, oriented at 45 degrees. That looks like it's horizontal. Okay, it's horizontal. Right? So if this is a horizontal filter, first thing that this is going to do, this is I naught right here. First thing this is going to do through the first filter is it's going to cut half of it because it's unpolarized light and it's a Polaroid filter. So the first thing that's going to happen is when I get here, in between the two filters, I'm going to be able to draw that the only remaining piece of that light is that one. Right? So this is, I'm going to call I1, and I1 is equal to 1/2 of I naught. Okay? And remember, I is the intensities. Okay? Now, when I take this next one here, and I say, okay, this one is now oriented at 60 degrees from the axis. So let's go 60 degrees from the axis. Which axis? Well, the one that goes this way, so I want it going kind of like this, but not that way. I want it going like this. No, that looks like it's parallel with that though. Okay, I don't want that. Let me try drawing it the other way. Let's try drawing it kind of, if it's that way, this way would be, I'm struggling to try and find a way that draws this such that it's seeable what I'm doing. That's not, maybe if I draw like this. All right, so let's say, like so. All right, so what I'm doing is I'm saying from the vertical, it's oriented. No, that's the wrong one. I want that to be 30, say. 30 degrees, that way. So from the vertical this way, no, let's do it this way. From the vertical this way, right, it's not oriented vertically, it's oriented 30 degrees off vertical. That's what I'm trying to get at with this thing right here, okay? So if I had a vertical Polaroid, it would be blocking completely. But this one has a slight bend to it, not bend, but a slight incline to it. And therefore that's going to allow some of this light to get through. Okay? The question is, how much? And the other question is, how do we orient this? All right? What we do is we're going to say what's coming out here at I2. Okay? Well, first off is that we're going to use I1 as our incoming light. The intensity I1 is the incoming light to Polaroid number 2 here. Therefore, I2 should equal I1 times the cosine squared of theta. But the question is, what's theta? Well, what we want to do is think about the angle with respect to the incoming polarized light. So if the incoming polarized light is, say, vertical, and I had a vertical filter, I want all the light to go through. Okay? If I have a horizontal polarized light and a horizontal filter, I want all the horizontal light to go through. Therefore, I need to think about what is the amount of light at an angle relative to the Polaroid filter. Okay? And that's the theta. Because every time I have these two things lined up, my cosine squared should be 1. the angle should be 0, right? If they're lined up, no matter if they're this way or that way or whatever. If they're lined up, the angle between the two is 0, and that's what theta is getting at. It's the relative angle between the incoming polarized light and the Polaroid filter, okay? In this case, I have horizontally incoming polarized light, and my filter is at a 30-degree angle from the vertical. That means it's a 60-degree angle to the horizontal, okay? It's a 60-degree angle to the horizontal. In this case then, theta is not 30 degrees. Okay, in this case, theta is 60 degrees. So just letting you know, be aware that just because you have an angle doesn't mean it's the one you're looking for. Okay? Now I've got a 60 degree angle here. The cosine squared of 60 degrees is, I guess, 1/4, because cosine of 60 is a half. Right? Sine of 30 is a half, cosine of 60 is a half, and I'm squaring that, so it's 1/4. So this is coming down to being 1/4 of I1. And I1, we know, is half of I0. So this is 1/4 of half of I0, which is equal to 1/8 of I0. And that's what the outgoing intensity is relative to the incoming intensity. All right, that's the kind of situation that you should be expecting to deal with when it comes to Polaroid and polarization, at least in terms of something like this where I'm shining Polaroid or unpolarized and polarized lights into things. Okay. Now there is another case in which polarized light is manufactured, and it involves reflection. So this is a pretty interesting situation, and it ultimately is the reason why you have sunglasses that are polarized. Or hopefully they are. You can go test, and I'll show you how to do that. Well, I already gave you the gas station trick. Light can be polarized by reflection, but it can also be polarized by scattering, okay? Now, outside today, it's cloudy, at least when I'm making this video. So maybe when and it's supposed to have a bit of rain perhaps tomorrow, which is Thursday. I don't know if it's going into Friday. Nonetheless, when there's a next day with blue sky, okay, if you have Polaroid sunglasses, try this. And by the way, you have to be kind of okay looking like a complete weirdo. But I guess this is Santa Cruz County, so shouldn't be too well noticed. What you're going to do is find the sun, right? Don't look directly at it. Just kind of point at it. And then make a 90-degree angle with your other arm like this and look that way. Now, if you have Polaroid sunglasses, start doing this with your head to turn the filter, right? That's what you're doing. You're turning the polarization axis of your glasses back and forth. And if they are polarized, you will see a darkening and then a lightening and then a darkening and then a lightening of the blue sky, because the sunlight coming at you, when it hits the upper atmosphere and makes the blue sky color coming down at us, it is polarized. So that's when I said typically most light is unpolarized. Most light emitted by something is unpolarized. However, if it interacts with something, natural light can become polarized. Okay? Sunlight is not polarized, but if it hits a surface or if it scatters off the blue sky, off the air molecules in the upper atmosphere, it can become polarized. And so that's a situation where naturally occurring polarized light happens. Okay? It's due to scattering. That's not a thing we're going to cover mathematically in this class because it's just a little bit beyond us. Actually, it's quite a bit beyond us, but that's okay. However, polarization by reflection is something that we can cover, but I see that we are just about out of time. Therefore, we will do this tomorrow, and I'll pick up with reflection polarization. I'll post the homework, and you can get started on some of the optical instrument questions, and there'll be some polarization questions as well. So that will at least be things you can go and do during all the free time you're going to have during your spring break. Anyways, with that being said, don't forget PLC 8 is Friday. I will post homework 5. Oh, and the quiz, if hopefully you're keeping up to date with the classes and you're watching this somewhere today, the quiz is up and running, and I posted it late yesterday. Not late, but like around noon or 2 or 1 or whatever. I posted it late yesterday. So I didn't give you the whole day. I'm giving you the whole day as well today, so it's midnight today for the quiz. All right. Okay. With that, I bid you good day. Happy Wednesday, and I will see you next time.